Hey class, this is Ms. Roberts at Shasta High School, and we're going to pick up some homework here that starts at question 32. Robert believes that the lines graphed at right are perpendicular to each other, but Mario, he's not convinced. So, how could we settle this amongst two friends? How do we know whether or not these lines are indeed perpendicular or not? So I'm over here, and the thing that we've talked about in class most recently is this whole idea that if two lines are perpendicular to each other, the rise and the run switch places and the signs change. Clearly, one of these is a negative slope, and this one has a positive slope. So yeah, the signs are different. That's good, but are the slopes reciprocals of each other? If I look at this one, this has a rise of 1 unit, and I can mark off a run of 2. So this has a slope of positive 1/2. The other line, if I start up here, I would say that it has a rise of -3, right? I just went down 3 units, and then I'm going to go over 2 units. So because this one has that down 3/2, this one has a slope of -3/2. These lines are not perpendicular to each other. If they were, their slopes would be opposite reciprocals. The line, if I wanted to sketch it, the line that would be perpendicular to this would be, it would have to be down 2/1. It would go through this point right here. And if I grab my ruler tool and bring it over to here, right? This line that I'm drawing right there, that would be the line that's perpendicular to it. And I can see that this line that I've drawn has a slope of -2/1, right? This line, the new line, has a slope of -2/1, and that line is the one that's perpendicular. The one that we had here, nope, those slopes are not opposite reciprocals, not perpendicular. And remember, go back to the idea that if we have the Cartesian coordinate plane and I rotate the entire plane about some point, and it doesn't actually matter where that point is, we're always going to observe that the rise and run switch places, right? What is a rise becomes the run and vice versa, and the signs are going to change. If you've got a negative slope, it's going to become positive. All right, so that's it. So Mario, way to be not convinced, right? Kind of looked like it at first glance, but -3/2 is not the opposite reciprocal of the number 1/2. Moving on, it says examine the rectangle at right. Write an expression for the perimeter in terms of x. Okay, that's fun. That's fun. So they told me this is a rectangle. So there's certain things I know, right? It's got 4 right angles, right? I know that my opposite sides are congruent, right? I'll mark these with tick marks, congruent. I'll write here a single tick showing that those are congruent. And I think the opposite, I don't know if it's definition, but these opposite sides are also parallel to each other. I don't need that information tonight. Well, if the opposite sides are congruent, certainly it has to be the case that this would be 2x and this would have to be x plus 3. So I can write an expression for the perimeter, right? The perimeter would look like a 2x plus an x plus 3 plus a 2x plus an x plus 3. So that's the perimeter in terms of x, and I certainly can simplify that. That's 1, 2, 3, 4, 5. There are 6 of the x variables there, and then I'm going to add plus 3. 3 plus 3 is plus 6. So that is an expression, 6 times x plus x, that represents the perimeter. And then it says, assuming the perimeter is 78 centimeters, determine the dimensions of the rectangle. Show all of your work. Okay, well, I've got this. So what I'm going to say now is that this is 200 and... No. They said that it's 70. I just forgot. I just saw it. Assuming it's 78, not 76. So it is 78. So this is an expression for the perimeter, right? 6 times x plus 6 is an expression, and this is the actual perimeter. So now the question is, find out what x is. Okay, so I'm going to subtract 6 from both sides. So I'm going to get 6 times x is 72, right? Right, 70 minus the 6, of course, is 72. And I'm going to divide that by 6. And I get that When I divide both sides by 6, I get that x is 12. So 12 is x, and I don't know that that's the answer to anything. It says, determine the dimensions of the rectangle. So if x is 12, that means that my rectangle has to be 24. That's just twice 12. 24 is that dimension, right? This is 24 also. And the other 12 plus 3, this has to be 15. And this has to be 15. So there we go, 24 by 15. And then finally, verify the area of this rectangle is 360 square centimeters. Explain how you know this. Well, if these are the dimensions of the rectangle, right, certainly the area of this rectangle is going to be that one dimension, 24 times 15. And if I do that, let's see, 24 times 15. Was it 360? Yeah, it is 360. I get that my area equals 360 square centimeters. Lots of tiny little square centimeters form the area of that thing. And I know that because I know the area of a rectangle is product of length times width. And we were told this is a rectangle. It's beautiful. It's good. All right, moving on, 34. It says write an equation for the tile pattern represented below. This is phenomenal. I love this because part of me is like, what tile pattern, right? There's nothing, literally nothing here, except there is something here. They're just using a couple different representations. So if I was to look at this and kind of create a table of values, I might say, okay, X is the figure, Y is the number of tiles. When figure 0, I don't know. Figure 1, I see it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 tiles. And the other thing that I know is ... We skip some. And then I can see, oh no, we don't skip 1, 2, 3. We don't skip a lot. We just skip the 2. We skip the 2. And we get the 3. Over here it tells us that figure 3, right, has 5, 6, 7 tiles. Oh, look at that. The number of tiles is decreasing over time. It's getting smaller. How much is it getting smaller by? Well, let's figure out the slope, right? 11, no, I'll do it this way. 7 minus 11 is the change in y. I did 7 minus 11 over 3 minus 1. 3 minus 1 is 2. 7-Eleven is a great place to stop on the way home from school and get a snack. But 7 minus 11 is the number -4. And 3 minus 1 is the beautiful number 2. So we have a slope here of -2. Okay, that's great, because I can fill in some values now. I can say, oh, 7 minus 2 is 5. That can't be right. It can't be right. Because I'm going backwards. Yeah, that's right. I'm going backwards. So if I'm going backwards, 7, I'd have to add 2 to go backwards in the pattern, right? So this would have to be 7, 8, and this would have to be the number 9. If I was going forward 4, that would be the 5, right? That was me going forward. But if I go backwards, I'm going to subtract 2. And then 11, 12, 13, there would have to be 13 tiles in the 0th figure. And that matters because that ends up being my y-intercept. So if I want, I could write the equation now. Y is equal to minus 2x, right? Minus 2 is my slope parameter. And then plus 13. That's my y-intercept parameter, and I got that from the table with little to no work. Just real quickly before I move away, I want to remind myself that there are 2 values that I know. 1 should give me 11 and 3 should give me 7. So it's just kind of nice to plug those in as a test. If I put the number 1 into here, this becomes -2. And -2 and 13 is 11. So that satisfies this point. And if I put in 3, -2 times 3 is -6. And -6 plus 13 is 7. 7. That satisfies this point as well. So this is definitely the equation that models this pattern. that was given to me with a couple different strange representations. Let's see. This next problem says, do not use your calculator. All right, I get you. I'm not going to use my calculator. The kitty hog-nosed bat, or bumblebee bat, is one of the world's smallest mammals. So tiny. It typically weighs about 2 times 3 to the negative third kilograms and has a 1.5 times 10 to the negative 1 meter wingspans. Okay. A giant golden crowned flying fox bat, on the other hand, typically weighs 1.6 kilograms and has a wingspan of up to 1.7 meters. Estimate how many times heavier the flying fox bat is than a bumblebee bat without using a calculator. Okay, so just conceptually, let's just say that one of them was heavy and it was 20, and the other one was heavy but not as much, it was 4. Well, if I did that, 20 divided by 4 would be 5. I would say that this number is 5 times heavier. So I'm just going to follow heavy or whatever. I'm just going to follow that pattern and use that to guide the arithmetic I'm going to do. So I'm going to take the weight, because this is how many times heavier. I'm going to take the weight of the flying box bat, which is 1.6 kilograms, and I'm going to divide that by the other one, which is 2 times 10 to the negative third kilograms. Okay, so I'm restricted here. I'm not supposed to use a calculator, so I'm actually going to do something that might look a little weird to you. I'm going to rewrite 1.6 is I'm going to write it as 16 times 10 to the negative 1. I know that looks strange, right? 16 times 10 to the negative 1. It's certainly true that that is 1.6, and I can do that without even thinking much about it. And I'm going to divide that by 2 times 10 to the negative third. I'm not supposed to make those look like x's. That's clearly just the multiplication. Well, what's nice about that is 16 divided by 2 is the number 8, right? I got 8 in my numerator, and then I've got these powers of 10, right? I got times 10 to the negative 1. And down below, I've got this 10 to the negative third. Well, I know how to move that 10 to the negative third. I can multiply both the numerator and the denominator by 10 to the third. That's going to give me in my numerator 8 times 10 to the second power. Oh, but I forgot the times 10. Geez. 8 times, it's not an x. 8 times 10 to the second power. And on my denominator, it's just 1. So I think 8 times 10 to the second, that's 8 times 10 times another 10 is 80. It's 800. 800 times heavier. The fox bat is 800 times heavier than the bumblebee bat. So that's and I just sometimes it's kind of liberating to think about powers like that, and I can just kind of move away from my calculator because I can reduce kind of big numbers to small numbers by just thinking about these powers of x. Moving on. Oh my God, this is the third night in a row we've had to do these. This is getting old. Uh, you know, I part of me is like, you know what? Hey guys, you're on your own on this one. And I really think you've seen me do this the last 2 nights, maybe 3 nights. I think you should be able to emulate that. And I want to encourage you, don't grab the calculator. Please try to do these the way that we talked about the last 2 nights, because the goal is to be able to manipulate these symbols. They're not always going to be numbers. Sometimes they're going to be variables that represent quantities, and we need to know how to kind of deal with those more complex situations. So I'm going to just leave these here. You can look up the answers on the CPM homework help if you want. I'm going to move on to this one. It says examine the figure graphed at right on the axis at right. What happens when you rotate the figure about the origin 90 degrees, 45 degrees, 180 degrees? What other, oh, let's take a look at it. So I've got this thing right here. And if I rotated this, let me kind of draw a couple extra lines here. I'm going to, and I'll make them very light. I'll make them a light gray. There we go. So if I was to line this up and say, let me just draw this line, that's nice. And I can, oh, I didn't quite hit the middle there, but I'll go like this line right here. That's nice. There we go, those little lines. So I know that this whole angle is 90 degrees. And if I was to rotate this thing 90 degrees, like this point would land at this point. This point would land. So everything's going to go back to the, oh no, 90 degrees. If I rotate the whole thing 90 degrees, this point's actually going to go all the way over to here, right? So it's going to become indistinguishable from the original figure because it's going to lock in place. If I was to rotate it a smaller number of degrees, just like 45, that point here is going to lock up and land into this place. So it still would be indistinguishable. Same thing with, so wait a minute, let's write those down. 90 degrees, it's going to land back on the same shape. 45 degrees, same thing. I could go 90 plus 45 is 135. If I did 135, this point would go all the way over to here. I don't know, it's 135 degrees. I can also do 180 degrees. The thing is I could do like where I just keep adding 45, right? I just keep adding 45 to it. So I know that 270 is going to be part of that. I know that 360 is going to be part of that, and there's a couple ones in the between there that I missed. So what it says, what shape will stay the same? Oh, by what other angle? Well, I just discussed that. I came up with a bunch of other ones, and then the other one is what shape will stay the same no matter how many degrees it is rotated. Well, that's fun, right? The shape is, of course, the beautiful circle. There's a circle, and you can rotate this thing all the time, and it's going to just look the same every single time it stops because it is a circle. All right, let's move on to that's the last question. Why are these? That's it. All right, I'm disappointed. Sorry about that. Sorry we don't have any more time, but that's the end of that. That's 37, and I'll be checking you guys out later. This is Mr. Roberts. Have a great evening.